Hey, grade 12s. So today we're going to our next lesson here. So it's finding probability using sets. And again, in the textbook, we're on section 4.3 if you want to keep up with that. I'm just going to make sure the mic is on there. So what we're going to cover today is actually quite a lot. This is a bigger lesson, but hopefully we can get through it in enough time. We're going to go over what an event space is compared to a sample space. And we talked about that before, but we're going to talk about an event space specifically being a subset of a sample space. We're going to talk about intersections and union of sets. And then we're going to talk about how to use Venn diagrams to help us solve different problems involving probability. And the first part of it, it's not going to seem like it's relevant to probability, but it actually is. And the last thing, we'll talk a little bit about what mutually exclusive events are. So a couple key terms. So a set, we talked about this before, but I'm just going to redefine it again, is a defined collection of distinct elements. So key word here is distinct, which means that we don't have repetition. So an example, if I have a set that has 1, 1, 2, and 3, technically that 1 is not really relevant, the extra 1 there. We only want to include 1, 2, and 3. We want no repetition. So we assume that there is no repetition at all in this set. Subset is a set whose elements are all elements of another set. So for example, 1, 2, 3 would be a subset of another set that would have 1, 2, 3, and maybe 4 or 5 or something extra, right? So essentially what we're saying is that all the elements that are in this set right here belong to this set over here. So an example here, 1, 2, 3, and actually I did the exact same one. So the set 1, 2, 3 is a subset of the set B, 1, 2, 3, 4, 5, because 1, 2, and 3 are all in the set B as well. So there's the next keyword we're going to talk about is a Venn diagram, and some of you actually might have heard of Venn diagrams before. It's essentially a way to visually illustrate the relationship between different sets. And this is something you might have even seen in maybe science classes, social science classes. So essentially what you do in a subset, in a Venn diagram, is you try to show how different elements might coexist within other sets. And so this example, 1, 2, and 3, for example, that's a subset, which means that it's inside of the set B, which is over here. So we can see that A is basically a smaller part inside of B. So a couple more examples of Venn diagrams. So this diagram here just shows a relationship, shows the definition, or not definition, characteristics of whales and fish, right? So we can see here that these are characteristics that belong to whales, but don't necessarily are not necessarily attached to fish. Vice versa here, we can see that these characteristics belong to fish but don't belong to whales. And then anything that's in between means that it belongs to both. Here's another one, just showing kind of the division in terms of different fruits and where they belong. So red fruits are obviously in this group. And these are just the ones that are only red fruits. Here are only the orange fruits, and here are the ones that are actually both, right? So we can see here that these have both properties. They're both orange and red. And then this is just a funny one here, just showing a Venn diagram. So what kids, dogs, and dads have in common. And we can see a little bit of overlap. So kids and dogs obviously eat things off the floor. That's just a joke here. And of course, the dads falling asleep on the couch, they have that in common with the dogs. Kids and dads, laugh at fart jokes, and all three of them want hot dogs for dinner. So that's just like a fun little Venn diagram, just showing the relationship between three different sets there. So sample space, the next definition here. So we know in probability that the event space is essentially part of a sample space. And again, the sample space is a collection of all the possible outcomes. So as an example, sample space for an experiment for rolling, let's say an experiment of rolling a die would be 1, 2, 3, 4, 5. So essentially the sample space is all the possible outcomes, right? So 1 all the way up to 6. And I think I just said 1, 2, 3, 4, 5. I forgot the 6 there. I apologize for that. And the event space for rolling a 3, let's say that you're only interested in actually rolling a 3 there, you would just write 3. And we can clearly see here that 3 obviously belongs in the sample space. It's part of that bigger set of all the possible outcomes. So again, key thing here is that all the event spaces will exist inside of a larger collection of possible outcomes, and that larger set of all possible outcomes is called the sample space. So essentially, the event space, which is the events that we're interested in, the outcomes that we're interested in, all belong inside of a sample space, which is a collection of all the possible outcomes. So in the Venn diagram shown, we can kind of see here, and I'm just going to show you what the Venn diagram looks like. We can see that obviously event A, this one right here, exists inside of a larger sample space, and normally the larger sample space, we denote it with an S, and instead of actually drawing a circle, we actually basically draw a big rectangle, which represents a giant sample space. So this whole big area that you see here, the big rectangle, is a sample space. And this right here is our event space. So hopefully you can see that writing. So this is our event space, this is sample space. And then note that I actually drew an A and then an apostrophe. And just keep in mind, what does that represent? That represents the complement. So what that essentially says is anything that's outside of this circle, that's the event space A, is not A. So this whole region here, I'm going to try to shade it a little bit differently. This whole region that is inside the sample space but not inside the event space, this is all called the complement. For some reason I can't right there. It's called the complement of A. So hopefully that kind of makes sense, and again, it shows a good illustration how to use the Venn diagram there. Intersection of sets. What we notice here is that we have two sets, and there's going to be some common area or like a shaded area in between where they overlap. So this overlap between two different sets is called an intersection. So we actually saw this in the first couple examples of Venn diagrams, that when we had the two different sets, there were actually some elements or some characteristics that were common to both. So this basically the area, the region where you have elements that belong both in A and in B, so they belong in both of them, that's called an intersection. And so by definition, if there is an element that's inside an intersection of A and B, then we know that the element is both in A and in B. So that's a really key word here. And the reason I bolded it, it's very, very, very important. In math, we are extremely picky about technicality. When we say both, we really do mean both. There has to be both in A and in B, okay? So an example here, a sample space, we have, sample space has 2, 3, 5, 8, 10, 12, and 15. And then we have the sets A is 2, 5, 10, and 12, and B is 2, 3, 8, and 10. And first thing we notice, went a little faster. First thing we're going to notice is that both of these sets, A and B, are subsets of S. And you can double check, you can make sure that all the elements here in A are all part of this bigger sample space, and you can check that all of the elements here in B are all elements of this sample space as well. So what we're going to do is we're going to draw a Venn diagram, and we're going to basically draw out where all these elements are supposed to go. So the first thing we notice is that A does have 2, 5, 10, and 12, but we notice right away as well that 2 and 10 actually belong to both of them. They're elements of A and B. So because they're elements of A and B, that means that it has to go right here in the intersection. So 2 and 10 need to go right in the intersection there. And then we notice that 5 and 12 only belong in A, but they don't belong in B. So that's why we wrote 5 and 12 in this little region right here. And it's really, really important that we don't write it in this area, because this is only for the intersection. So keep in mind that this is the intersection of A and B. And again, this is a symbol we use for intersection. Basically, it looks like it's a U facing down, right? And then we look at the other elements in B that don't belong to A. We can see here that 3 and 8 are in B, but they're not in A. So because they're in B but not in A, we make sure that we write them in this region that's B, but not including this intersection. So we're just being really, really careful. And sorry, for some reason, it's not letting me write it there. We're just being really careful to only include it in this region and not in the intersection, okay? So it's in B, but not in A. And then, are there any other elements that we missed here in the sample space? Well, we have 2 covered, 3 is already there, 5 is there, 8 is there, 10 is there, and 12 is there. And then you're going to notice that 15 is in the sample space, but it's nowhere here. So where do we place it? Well, if it's neither in A or if it's in neither A or B, then we actually place it outside of both circles. And it doesn't actually matter where you place it as long as you place it not in the circle, but still in the rectangle, right? So you don't want to draw it outside because it's still part of the sample space. And again, the big rectangle represents the sample space, but it cannot be in the circles because in either one of the circles because it's not an element of A or B. So that's an example of how we draw a Venn diagram. So to answer this question, it asks us for the set A intersection B. So what are the elements that are in A and in B? Well, there's only 2 of them there, 2 and 10, and we are done. So our next definition is disjoint sets. So what are disjoint sets? So disjoint sets are basically 2 sets that have no common elements. And in this case, what we're basically saying is that the intersection of the 2 elements, since there's no overlap, there's nothing there. So we can see here that A and B are disjoint. There is no overlap between them. There should be some sort of overlap. Normally we'd see that, but in this case, it's an empty set, right? And an empty set, what that really means is that there are no elements there. And we write it 2 different ways. We can either say that the intersection of A and B is simply the empty set, and that's what this means right here, empty set. Essentially means that there's no elements there, or we can simply write it as the number of elements in A and B is 0 because there's nothing there. And the next definition we'll go over is a union of sets. So let's say that we have 2 sets just like the previous example, and we are instead of focusing on the intersection, we're actually going to focus on basically the union of the 2 sets, which essentially means that we are including all elements that are in either A or B. So the key word here is or. And again, in English, I feel like in everyday language, we tend not to make a big difference between and or, but in math, we are very particular about what that means. When we use or instead of and, what that means is that you don't necessarily have to have an element that's in A, you have an element that's in both A or B, sorry, A and B. What we mean to say, and again, it's confusing myself because again, in everyday language, we interchange or and. But essentially what we're saying with the union of 2 sets is that as long as the element is either in set A or in set B, it is part of the union. So what we're saying with the union is that it's any element that is inside of this whole entire circle region, right? So it can be anywhere in B, and it can be in the intersection, it can be in B but not in A, or in A but not in B, doesn't matter. As long as it's in this area, it's part of the union. So the union is a lot less selective about what you can include. So it's essentially saying as long as you have an element that's in either A or B, then it's definitely part of the union. And the symbol that we use for that is almost like a U shape opening up. So let's look at an example here. It's probably a lot easier once you look at a concrete example. So for the Venn diagram that's shown here, we need to determine the following sets. So let's find P intersection Q, the union of X and Q, and let's start with the first one. So I'm going a little too faster, sorry. So let's start with P and Q, the intersection of P and Q. So what are the elements that are both in P and in Q? Well, we can see here that here's P, and here is Q. And actually, I'm going to switch colors just so you can kind of see a difference. Let me see here. Let me see. Sorry, I apologize. I'm just doing this. Normally I have a bit more time, and I feel like I might be a little rushed, and I apologize for that. But hopefully we're still able to get through the majority of the lesson here. So we can see here that P and Q are the two regions that I drawn. So P is in red, Q is in blue. And now really what I'm doing is just trying to figure out what elements are in the intersection of both. And I can clearly see here that 6 and 9 are in both of them, right? So since 6 and 9 are in both of them, that means that a P intersecting with Q is 6 and 9. And I just write the set with proper notation. Make sure you use the curly brackets here. Now the next one, X and Q. So I'm going to switch colors here so you can see a little bit of a difference. I'm going to make this green here, and it says X with the union of X and Q, not intersection. I apologize if I said that wrong. So now we're looking at the union of X and Q, and the union of X and Q basically means list out all the elements that are either in X or they're in Q. They don't have to be in both of them. They just have to be in one or the other, right? So in this case, we actually have a lot more. So we have 4, 2, 9, 10, 12, and 6. So there are a total of 6 different elements that are in either X or Q. So for the union of sets, X and Q, we have 2, 4, 9, 10, 6, and 12. And I know I didn't write it in order, but I was just basing it off of what I saw first. So that is our answer there. So the next part, the additive principle of union of sets, this is where we start kind of piecing everything together. So this might actually, the first time you see this, it might look confusing, but I think ultimately it should make logical sense. So when we're counting the number of elements that are in either A or B, so just to give an example here, remember this is the union of A or B, this whole giant region here in green. The issue that we run into is that there are some elements, and I'm going to just pretend that these are just little elements. There are some elements that are actually in both A and B. So if we were to count all the elements in A, and then we count all the elements in B, and I'm just going to make this up, let's just say there's 4 elements here, 4 elements here. The issue we are going to run into if we count every single one of them individually is that we're going to count twice by accident. So if I count all the ones in A and then all the ones in B, I actually end up double counting the ones in the middle. I hope that kind of makes sense, because if I count the ones in A, automatically includes the elements in the intersection. If I count all the ones in B, I already include the elements in the intersection. So I'm counting twice. So to make up for this difference, when we count the union, when we count the number of elements in the union of 2 sets, we make sure that we subtract off the intersection so that we make up for the fact that we overcounted. And again, this makes a little more sense with a more clear example. So let's go through this next one here. So in this example, we're trying to find the number of elements in A union B, given that the set A, sorry, I'm having some computer issues today. The set A is 1, 2, 3, 4, 5, 6, and set B is 2, 4, 6, 8, 10. And we're going to use the additive principle. Now, there are 2 different ways to do this. One way, obviously, is just to directly figure out what are all the elements that are either in A or B, and just keep in mind that we never repeat when we're writing sets, right? So you could go through this list and say, okay, I got 1, 2, 3, 4, 5, 6, not 7, but then I have 8, and then I have 10. Done. So I already technically have it written out. We can definitely do that, and I'm just going to write the answer up here. We might as well write it out. So it's 1, 2, 3, 4, 5, 6, and then we said 8, and then 10. So technically I'm done, right? So you can look at this and be like, that's a pretty easy question. I already know the answer. It's a total of 8 elements because there's there's a total of 8 because there's 8 elements in this set. But let's use the additive principle to illustrate what we mean by this. Okay, so the first step is we notice that the the set A has 6 elements inside. So we write that as NA is 6. We can see here that there are 5 elements in the set B. So we write that as the number of elements in B is 5, right? So NB is 5. So if we want to find the union, first what we need to do next, or the next step after this, is find out what the intersection of A and B is. So let's look at our list here and figure out how many elements are repeating here. So we notice here that we have 2, 4, and 6 that repeat in both A and B. So that means that the intersection of A and B is 2, 4, and 6. So the number of elements in the intersection is 3. So let's put this all together. Using the additive principle, we know that the number of elements in the union of A and B will be the number of elements in A plus the number of elements in B minus the number of elements that are in the intersection of A and B. So what we have here is really just the number of elements in A, which is 6, plus the number of elements in B, which is 5, minus the intersection, there are 3 elements in the intersection. So that gives us a total of 8. And notice we got the exact same answer up here. We already counted it out. We knew that there were going to be 8 elements in the union. So we get the same answer either way. And again, it seems very easy, and you're probably thinking, why do we have to go through this if you can just count on your own? Because this is a very easy example. We are eventually going to do some tougher ones where it's not going to be that easy for you to count it out. Sometimes you don't have the set all listed out. So all you're given is maybe a probability, or you're given some different information, but you're not actually given the sets themselves. So you can see here, using an easy example, how powerful this principle will be. So let's look at a word problem. So there are 200 grade 12 students at a school. 120 of them take data management, 110 of them take calculus and vectors, and 70 of them take both. How many grade 12 students are taking neither data management nor calculus and vectors? So I'll just repeat everything just to make sure everyone's kind of following along. So 200 total students just for grade 12s, and 120 of them take data management, and 110 of them take calculus. And keep in mind that there are 70 that take both. So there's a group of students in this school that are not taking either course, right? So the first thing I would recommend doing is actually drawing a Venn diagram to keep track of all the information. So I'm gonna start by making this a little bit easier for myself. I'm gonna, instead of writing data management, I'm gonna write D, okay? So the set D is the set of students that take data management. The set C is a set of students that take calculus and vectors. And obviously, we're told that 70 of them take both. There's going to be 70 elements or 70 students that are actually going to be in set D and set C. I hope that kind of makes sense so far, right? And altogether, the number of elements in the sample is 200 because that's the total number of students that we have. Grade 12 students. And so what we're going to do here is we're going to draw a Venn diagram to kind of help us out. So first thing I would do is put a nice little rectangle around it, because again, this is going to represent the sample space. We know that the total sample space is 200. And what else are we given? We're told that the students that take data management, so this whole little group here, is 120. And we have more people in data management than calculus and vectors, just saying, that's good. And so what we're going to do in this case is we're simply going to fill in the rest of the information based on what we have. So we're told that there are 70 students. Oops, sorry, got the eraser there. We are told that there are 70 students that are in both courses. So the 70 students are right here in between. So what we need to do at this point is simply figure out the number of students that are, before we even get to the number of students that are taking neither course, I would actually start off by just finding out how many students are taking either calculus or data management. So what we're going to do is we're actually going to use the additive principle to figure out what the union of the data management set and the calculus set will be. So this is our next step. So we're essentially going to find out how many elements or how many students are in this union, which is the green area right here. And then we're going to take that away from the 200 to find out how many students are taking neither. Because this is really what we're trying to find. We're trying to find the number of students that are in neither one of these bubbles. So 200 is a total amount, but there's a group of students that are in neither bubble. They're just outside of it altogether. That's what we want to figure out. How many students are in this outside region? So let's go step by step. So first, what we're going to do is find out what the number of elements in the union of the sets are. So we have the union of D and C, which is going to be the number of elements in D. So the number of students taking data management plus the number of students taking calculus. I don't know why the computer's being crazy today. And the number, and then we're going to subtract off the number of students taking data management and calculus, right? This is the intersection. So that gives us 120 plus 110 minus 70, which is a total of 170. So that means that there's 170 students that are taking either data management or calculus. So now we just work backwards a little bit. So if there's 170 students taking either data management or calculus, what does that mean? So going back to our Venn diagram, if we know that this union, I'm going to write this down like this, the union is 170. So there's 170 students that take either data management or calculus and vectors. That means that there are a total of 200 minus 170, 30 students that are taking neither course. Okay, so I hope that kind of makes sense. So all we do is kind of work backwards there. So obviously the number of students that are taking neither one of the courses, calculus nor data management, is 30. And that's it. So let's look at a probability, let's look at how this connects with probability, because this is the part where people get a little confused. They're like, this is, I mean, this makes sense, maybe, hopefully, but you don't really get the connection with probability. So now we're going to connect it up. So if we are given two events, A and B, the probability that either A or B occurs is simply given by what you really expect. It's the same additive principle. The only difference is that there's probability here. The probability that A or B happens, and again, keyword here or, so it's either in A or it's in B. It doesn't have to be in both of them. Is the probability that A occurs plus the probability that B occurs minus the probability that A and B occurs together, okay? And again, a reminder that when we see the intersection, that's a strict and. It has to, A and B have to occur. So if A and B have no outcomes in common, so let's say that they are mutually exclusive events, and that's a key word here, that means that the intersection probability of the intersection is actually going to be 0 because there is no overlap. So if there is no overlap, so again, I think we looked at a couple examples earlier, disjoint sets. If there is no overlap, then that means that the probability of A and B occurring, so the intersection, is just going to be 0. So that means that this formula actually reduces a lot more. It actually is simply the probability of A or B is just a probability of A plus a probability of B. And that's all you really need to know there. So let's look at another example. So we have a researcher that's looking at two bug characteristics known as X and Y, and they examine 100 insects. Of the 100 insects, 80 of them have characteristic X or Y or both. The researcher can't determine directly whether an insect has characteristic Y alone. 48 have X and 23 have both X and Y. So a lot of details in this question, but let's just go step by step. So what do we know so far? So before we get to that, what are the questions here? So what is the probability that an insect chosen at random has characteristic Y? And then the second question is, what is the probability that an insect chosen only has characteristic Y? So let's look at the solution here. So the first step, if we want to find out the probability that we have an insect that has characteristic Y, and again, they can have characteristic Y and also X, it doesn't matter, but as long as we have characteristic Y at some point, right? That's what we're interested in right now. So what do we know so far? Well, we know in the question that the probability that the insect has the characteristic X is 48 out of 100, and Y is a 48 out of 100 because 48 of them have X out of the total 100, okay, which is a sample space there. We know that the probability that it has x and y is 23 out of 100, and y is a 23 out of 100 because we're told that 23 of them have both x and y. So that's still pretty easy so far. And the last one, the probability that we have x or y is 80 out of 100, and y is 80 out of 100 because we're told that 80 of them have characteristic x or y, or both, right? So that's including that's basically the union. So what we're going to do is we're going to work backwards to figure out what P of the probability of y is. That's really what we're trying to do. So what do we know so far? Well, let's use the additive principle to help us figure this out. So we know from the additive principle that the probability of x or y, remember that the u opening up is x or y, is the probability of x plus the probability of y minus the probability of the intersection of x and y. So let's go step by step here. So we know the probability of the union is 80 out of 100, or 80%. So we replace it here. The probability of x is 48 out of 100. The probability of y is unknown, right? We have no idea what this is, but we're going to figure that out. And then all we're going to do is subtract off what the probability of the intersection is. And our next step here is to simply do a little bit of math. We have two fractions on the same side, so we're definitely allowed to join them up together. So 48 over 100 minus 23 over 100 gives us 25 over 100. And now our next step here is to simply isolate for the probability of y. So we're just using a little bit of algebra here. So using algebra, we know that if we want to isolate for the probability of y, so that means that we need to bring the 25 over 100 over to the other side. So we subtract off 25 over 100, which gives us 55 over 100, and that means that the probability of y is 55 over 100. For the second part, we want to find the probability that the insect has characteristic y, but it doesn't have the characteristic, but it only has the characteristic y, it does not have the characteristic x. So because we're trying to find out what the probability of having y is, but not having x, we're being a little bit more picky about this, right? So it might be easier, instead of going straight to probability, to actually look at it in terms of counting the numbers, right? So we're essentially trying to find all the insects that have characteristic y but don't have characteristic x. Well, what do we kind of notice? All we really need to do is simply subtract off the number of insects that have both, right? Because we already know how many insects have a characteristic y. We just have to subtract off the intersection there. So I'm going to draw a little picture here so you can kind of see what I mean. So this is x and this is y. We're essentially saying that we are interested only, and I'm just going to switch the color. We are only interested right now in finding out how many insects are in this region right here. So it's in y, but very strictly not in x at all, right? So all we really want to do is simply subtract off the intersection of x and y. So this right here is the intersection of x and y, and really what we want to do is subtract that intersection from y. So hopefully that kind of makes sense. So we're going to take the number of insects that are in y, and we're going to subtract off the intersection. We already know how many insects have characteristic y. We already found that in the other question, 55, and we're subtracting off the number of insects that have both, which is 23, and that ends up giving us the number of insects that only have y, which is 32. And that means that the probability of choosing an insect that only has characteristic y is 32 out of 100. And that's it. So hopefully that made sense. And then here is the classwork. I apologize. I feel like that lesson was a bit rushed. There was a lot of material to go through. Hopefully I didn't rush it too much.